was younger. And everybody say, I was taking way back. And everybody say, I when I was younger.
Now on to vector valued, and we're going to do the opposite of differentiation, so we're going to do integration, okay? And again, just like differentiation, a lot of the things that you've learned in calculus so far, they're going to remain the same. We're just going to be working with vectors now. Okay, so what we're going to do is take the integral of something, and let's say we have an r of t, okay, dt, and this is going to be equal to, if r of t, okay, so I'll write down here, if r of t is given by our normal x of t, y of t, and z of t, this is what's going to happen. So remember how when we took the derivative of r of t, we had to take the derivative of each of its components or coordinate equations, right? Or you can also call them parametric equations, right? So anyways, what we're going to do here is take the integral of all of them. So we're going to integrate, so we're going to get a integral from a to b of x of t dt, comma, integral a to b of y of t dt, and lastly, integral from a to b of z of t dt. Okay? Perfect. It's kind of self-explanatory. I mean, once you see this, then you can just go through and do the calculations. Also, what's important to note is that if r of t, capital R of t, is equal to the integral of little r of t dt, then this big R of t is called the antiderivative. Okay? And you've probably seen this from previous math classes. And I cannot spell. Derivative. There we go. Okay, so this is called the antiderivative of r of t. Okay? Alright, so this actually, from the antiderivative part down here, we can get something important from those. So let's say if we have two antiderivative functions, if p of t and q of t, capital Q of t, things are getting serious. We're using capital letters now. Now those just mean that they're antiderivatives of something. If they are differentiable, and I'll abbreviate differentiable, and this is a big one, the derivative of p of t and q prime of t, if they are equal, then that means that p of t is equal to q of t plus a constant vector. Okay, so this thing here, that's called a constant vector. It's kind of like, again, when we've worked with calculus things before, it's like when you anti-differentiate, or if you take the integral of something and you need that initial condition, right? And sometimes you have that plus c, but now that plus c happens to just have an arrow over it because we're dealing with vectors. Okay, so this is true because, and here's the reasoning behind it. This means that ddt of q of t plus this constant vector. Okay, so if you take the derivative of this, and constant vector, that just means it's it doesn't have any variables in it, right? So like let's say our constant vector is 1, 2, 3. Okay, so when you differentiate that, the whole concept behind that is that when you differentiate a constant vector, just as if you were to differentiate a constant number like 2, then that goes away in the differentiation. Okay, and then we just get q prime of t. All right. And if you differentiate p of t, so this would be the left side. So I'm just comparing differentiating the right side with differentiating the left side. Okay, then this is just going to turn out to be p prime of t. So these ultimately are equal. Okay, so I'll just write a big equal sign there. So these are ultimately equal. Okay, so when vector valued functions are differentiable and their derivatives, their first derivatives, are equal to each other, that means that they differ, the original vector valued function. So for example, here we had p of t and q of t, then those are exactly the same except for they might differ by a constant vector. Okay, alright, so now for the last topic for this video. It's called the fundamental theorem of calculus, and you've probably seen this, the FTC, fundamental theorem of calculus, but we're going to add on 4 vector valued functions. Okay, lots of abbreviations going on here. Okay, so what it says is if r of t is continuous on the interval, we're going to make it AB because we like the beginning of the alphabet, and r of t, so this is capital R of t, is an antiderivative, and antiderivative, went better the second time, of r of t, of this aforementioned r of t, then we have the following. Then the integral from a to b of r of t, little r of t, dt, is equal to r, capital R, evaluated at b, minus capital R evaluated at a. Okay, so we've seen this before. I mean, it's not that new of a concept, hopefully. It's kind of more or less like if f, capital F, is, not without an arrow, sorry, if capital F is a function, is an antiderivative of f of t, little f of t, then the integral from a to b of f of t, little f of t, is equal to capital F evaluated at b minus capital F evaluated at a. So that on the bottom there, that's just a relation to scalar valued functions, the ones that we're usually used to, right? And this is our new one for vector valued functions. Okay? So that's basically it. I hope that helped as an overview of the calculus of vector valued functions.
Your head and I paid, so I got it made, but didn't always have clout. Used to live in South Central LA, that's where I stayed.